Hi everyone, this is NLP Corgi. Today's deep dive is about the paper from Shanghai Innovation Institute and MOSI Intelligence MOVA towards scalable and synchronized video-audio generation. Modern video models can paint stunning visuals, but most of them are effectively silent movies. When sound is added, it's usually through a separate audio model that works after the video is done. That cascaded setup is fragile, errors compound, synchronization drifts, and it's expensive to run. Meanwhile, the most capable joint audio-video systems, like Sora and Veo, are closed, so the community can't really study or extend them. This paper introduces MOVA, an open, large-scale model that generates video and audio together, with synchronized speech, sound effects, and music. MOVA is designed to feel like a full audio-visual engine, not just a video model with some noise on top. It can generate lip-sync speech in both English and Chinese, including multi-speaker dialogues where different voices stay attached to the right faces. It produces physical sound effects that line up with what you see on screen, like impacts or footsteps, and it can render scene text directly into the video. The system supports both landscape and portrait formats, so it targets everything from cinematic clips to mobile-style content. At a high level, MOVA is a 32 billion parameter mixture of experts model, with about 18 billion parameters active during inference. It takes text and optionally an initial image frame, and generates both video and audio in one coherent pass. The authors don't just describe the model, they release the weights, the training code, and an inference and fine-tuning stack, so others can build on it or adapt it to their own domains. Architecturally, MOVA is built around two strong unimodal backbones. For video, it reuses the WAN 2.2 A14B diffusion transformer. For audio, it trains a 1.3 billion parameter text-to-audio diffusion model with a similar design. These two towers don't just run side by side. They're coupled by a 2.6 billion parameter bridge module that injects video features into the audio stream and audio features into the video stream through cross-attention. To keep the timing consistent, they use an aligned rotary positional encoding so that audio and video tokens that correspond to the same physical time share compatible positions, even though audio is much denser in time than video. Under the hood, MOVA doesn't operate directly on pixels or raw waveforms. It uses a video VAE from WAN 2.1 to compress frames into a spatiotemporal latent grid, and a DAC-style audio VAE from Hunyuan Video Foley to compress 48 kHz mono audio into a compact latent sequence. The diffusion transformer then works in this joint latent space. Training uses a flow matching objective. At each time step, the model sees noisy versions of the video and audio latents and learns to predict the velocity that moves them back toward the clean data. The loss has separate terms for video and audio, with weights that control how much each modality contributes during training. One subtle but important problem is that audio and video live on very different temporal grids. Video latents might represent 24 frames per second, while audio latents are far more frequent. If you just assign positions independently, cross-attention can end up matching a sound to the wrong frame. MOVA fixes this with an aligned rope scheme. It rescales the video time indices into the audio time units, so that tokens that correspond to the same physical moment share compatible positional encodings. That way, when the bridge attends across modalities, it naturally lines up events in time instead of drifting. To make this architecture actually learn synchronization, the authors needed a lot of clean, well-labeled data. They start from several public datasets like VGG Sound, ACAV 100M, Open Human Vid, SpeakerVid 5M, and others, plus large in-house collections. All videos are standardized into 8.05 second clips at 720p and 24 frames per second. Then they filter aggressively. They drop clips with poor audio, low video quality, or weak audio-visual alignment. Finally, they run a multimodal captioning pipeline that separately describes the video, transcribes speech, and captions non-speech sounds, and then merges those into a single, semantically rich caption per clip. The data pipeline is deliberately staged. In stage 1, they clean and normalize the raw videos, crop to core content, enforce 9:16 or 16:9 aspect ratios, and segment into fixed 8.05 second windows using voice activity detection and scene change detection. In stage 2, they score each clip for audio quality, video quality, and audio-visual alignment, and discard anything that doesn't meet their thresholds. In stage 3, they run separate captioners for video and audio, then use a large language model to merge those into a single coherent description. By the end, only about a quarter of the original video duration remains, but what's left is high quality, synchronized, and richly annotated. Before coupling audio and video, the authors first train the audio tower on its own. It's a 1.3 billion parameter diffusion transformer trained to generate audio from text across 3 domains: general environmental sounds, music, and speech from TTS-style data. Each training clip comes with a text prompt and an explicit duration token, so the model learns to control length. On the audio caps benchmark, this audio model matches or beats strong baselines like Audio LDM2 in several metrics, including inception score and KL divergence, and it scores best on some human-oriented audio box metrics like consistency and perceptual quality. Quantitatively, the audio tower holds its own. On audio caps, its Frechet distance is on par with Audio LDM2, but its KL divergence is lower, indicating a closer match to the real data distribution. Its inception score is substantially higher than Audio LDM2's, suggesting more diverse and high-quality samples. On the audio box benchmark, it achieves the best scores in consistency and perceptual quality, which are closer to how humans judge audio. This gives MOVA a solid audio backbone before any cross-modal training begins. Once both towers are ready, the authors train the full joint model in 3 phases. Stage 1 runs at 360p resolution on a very diverse dataset, with aggressive noise on video and milder noise on audio, plus heavy text dropout to force the model to rely on cross-modal signals. Stage 2 stays at 360p, but switches to a quality-filtered dataset, aligns the audio noise schedule with the videos, and adds loudness normalization to stabilize audio under guidance. Stage 3 then scales up to 720p, using only the highest quality clips. All 3 stages are trained end-to-end on 1024 GPUs, totaling around 43,000 GPU days. Training a 32 billion parameter joint model is tricky. The authors choose to optimize everything end-to-end from the start, rather than freezing the towers and only training the bridge. To keep things stable, they use a higher learning rate for the bridge and a lower one for the pre-trained towers, so the bridge can learn quickly without destroying the unimodal priors. They also decouple the noise schedules for video and audio, letting each modality follow its own denoising trajectory. On the system side, they rely on fully sharded data parallelism and sequence or context parallelism, plus careful memory management to reach about 35% machine flop utilization at scale. At inference time, MOVA uses an extended form of classifier-free guidance. Instead of a single guidance strength, it treats text and cross-modal information as 2 separate conditions. One guidance scale controls how strongly the model follows the text prompt, and another controls how strongly it enforces alignment between audio and video through the bridge. By tuning these 2 knobs, you can trade off between perfect semantic adherence and very tight synchronization. In some settings, this reduces to standard 2-branch guidance, but the full 3-call version gives the most flexible control. The user-facing workflow is also layered. A user can provide a text prompt and optionally a first-frame image. First, a vision language model, Qwen3VL, analyzes the image and produces a structured description of style, cinematography, visual elements, and any on-screen text. Then a large language model, such as Gemini 2.5 Pro, combines that visual description with the user's text to synthesize a richer, training-style prompt. Finally, MOVA takes this enhanced prompt plus the initial frame and generates the full video and audio. If no image is available, they simply feed in a blank image and rely on text alone, which still works surprisingly well. To evaluate MOVA, the authors use both existing and custom benchmarks. They adapt VerseBench, which originally focuses on images and text, by adding audio descriptions to create joint video-audio prompts. They also build a new benchmark that covers 6 realistic scenarios, including multi-speaker dialogues, movie-style clips, sports, game streams, camera motions, and anime. On the metric side, they measure audio quality, semantic alignment, temporal synchronization, and lip-sync precision. And because current metrics don't fully capture human perception, they also run an arena-style human preference study, where viewers compare pairs of videos and an ELO rating system ranks the models. On VerseBench, MOVA is compared against 3 strong baselines, LTX2 and OVI, which are joint audio-video generators, and a cascaded system that pairs WAN 2.1 for video with audio for audio. MOVA's 360p and 720p variants generally achieve higher audio quality scores and better semantic alignment than the joint baselines. When dual classifier-free guidance is enabled, MOVA's desync and lip-sync metrics improve further, approaching or matching the cascaded pipeline's temporal precision, while still benefiting from a unified architecture. The cascaded system retains a slight edge in raw desync, but MOVA narrows that gap significantly. The authors systematically vary the bridge guidance scale, called SB, to see how it affects behavior. As SB increases, metrics that measure synchronization and cross-modal alignment, like desync, image bind score, and lip sync scores, consistently improve. However, there's a cost. Speech quality metrics like DNS-MOS degrade slightly, and automatic speech recognition accuracy, especially in multi-speaker settings, gets worse. In other words, pushing the model too hard to align audio and video can make it less faithful to the exact text instructions or speaker tags. This makes SB a meaningful knob for applications that care more about one side of the trade-off than the other. Interestingly, MOVA is trained primarily on image plus text conditioning, but it also works well in a pure text-to-video audio mode. To test this, the authors simply replace the reference image with a blank placeholder at inference time. In this T2VA setting, the model still produces synchronized video and audio, and in some metrics, like inception score and desync, it even outperforms the standard configuration. Identity-sensitive metrics like lip sync confidence drop a bit because there's no explicit face geometry to anchor to, but overall the results show that MOVA has learned a robust joint prior that doesn't strictly depend on an initial frame. In the human evaluation arena, MOVA comes out clearly ahead. Using over 700 prompts and more than 5,000 pairwise votes, MOVA 720p achieves the highest ELO rating among all tested models. It wins the majority of comparisons against LTX2, and more than 70% of the time against OV and the WAN plus MM audio cascade. An internal ablation shows that using the prompt rewriter, this multi-stage enhancement pipeline significantly improves human preference scores, confirming that aligning user prompts with the training style distribution really helps the model shine. Lip synchronization is one of the toughest tasks in this space. Unlike a single impact sound that just needs to line up with a visual hit, speech requires continuous, frame-by-frame coordination between mouth shapes and phonemes. The authors track lip sync metrics across their 3 training stages. At 360p in Stage 1, the model quickly learns basic alignment. Stage 2, still at 360p, but with better schedules and data, significantly boosts confidence and reduces error. Stage 3 then scales to 720p, and rather than breaking synchronization, it refines it. Lip sync metrics plateau at strong values, showing that the model can handle higher resolution without losing temporal precision. On the system side, the authors pay close attention to efficiency. At 720p, the sequence length is large, so they increase context parallelism to 16 to keep memory under control. They avoid redundant computation by running the VAEs once per context parallel group and broadcasting the latents, instead of recomputing them on every shard. They also manage Python's memory manually to avoid garbage collection stalls, and they port the stack to Ascend NPUs with fused attention and rotary embedding kernels. These engineering choices are what make multi-week, 1000 GPU training runs feasible. Despite its strengths, MOVA has clear limitations. The 1.3 billion parameter audio tower struggles with the most demanding audio, like rich music, singing, or complex textures that need long-range structure. Multi-speaker scenes can still confuse who is speaking when, especially with rapid turn-taking or overlapping speech, partly because diarization and active speaker labels in the data aren't perfect. Training and inference are expensive, and clips are limited to about 8 seconds. Finally, the model doesn't explicitly reason about physical sound propagation, so effects like the delay between lightning and thunder aren't guaranteed to be correct. To wrap up, MOVA shows that a carefully designed dual-tower architecture, coupled through a strong bridge and trained on a large, high-quality dataset, can deliver high-fidelity synchronized video and audio. The work highlights how important data curation, temporal alignment mechanisms, and training schedules are for lip sync and general audio-visual coherence. By releasing the model, the code, and detailed benchmarks, the authors aim to make MOVA a solid open baseline for future research in fully audiovisual generative models.